Add the PowerPoint. So if you go to your files folder, there will be in number 5. In that we have heat and mass transfer chapter 3. So we can download that, then we can discuss. Yes, is the PowerPoint is visible to you?
Yes, sir.
Okay, fine. So then we can start. So in this class, we are going to discuss about the unit number 5, heat and mass transfer. In that we have to discuss about the last portions, heat exchangers, right? Flow through heat exchangers, then LMTD of a heat exchanger, then AMTD of a heat exchanger. Then in that we have two different types of heat exchanger, like parallel flow, then counter flow. So all these we are going to discuss in this class. So the performance and analysis of counterflow and parallel flow heat exchangers also to be discussed. Then LMTD and effective LMTD, AMTD, and effectiveness of the heat exchangers to be discussed. So introduction about the heat exchanger. So need for the heat transfer. Actually, heat transfer that you know very well. To heat a cooler fluid by means of hotter fluid is the need here in heat transfer. Then to reduce the temperature of the hot fluid by means of a cooler fluid also they need. Then to boil a liquid by means of a hotter fluid. Then to reduce the gaseous fluid by means of a cooler fluid. Then to boil a liquid while condensing a hotter gaseous fluid. So these are the needs of a heat transfer. So for that we have heat exchanger. So let me see what is heat exchanger. So when energy as a heat has to be transferred from one stream of a fluid to another, both fluids are directed through an apparatus known as heat exchanger, right? So if you want to transfer heat, we need this heat exchanger, right? So the two streams are separated by a barrier. Then there will be no mixing, right? So normally the wall of a tube or pipe through which the heat is transferred from a fluid at a higher temperature to the colder one. So actually we can pass the fluids with the two different temperatures. So one will be having high temperature, then another one will be having low temperature. So this, if you pass these fluids through two different chamber, when we attached both the walls or tubes of the heat flowing channels, so there may be a chance to exchange the heat, right? So that is the principle here. So heat exchanger is an adiabatic steady flow device in which two flowing fluids exchange or transfer heat between themselves due to a temperature difference. So this is happening because of the temperature difference. We are using two different temperature fluids, so without losing or gaining any heat from an ambient atmosphere. So we no need to take the atmospheric temperature to heat or cool the fluid, right? So this is the line diagram of the heat exchanger. So we have to pass. So we have to pass hot fluid in one channel, and we have to pass cold fluid in one channel. So because of some contact, because of the profile of the tube or the profile of the wall, so we can transfer heat. Right. So with the use of this, so this equipment or this apparatus is called as a heat exchanger. Right. So actually, this heat exchanger is an insulated device. So some examples of heat exchangers are tabulated here. So there will be a steam condenser. So in this steam condenser, so steam heat exchanger occurs between steam to cooling water. Right. So you can transfer. So actually, you know very well. So steam is having high heat, high temperature. Then this heat is transferred to the cooling water in this steam condenser. Then we have economizer. So in that economizer heat exchanger, the flue gases will transfer heat to the feed water. Then in superheater also there is flue gas. So that flue gas is having high temperature. That high temperature is transferred to the saturated vapor. Then in superheater also there is a flue gas. Yes, flue gases. Then that is transferred to saturated vapor. Then cooling tower. So cooling tower. So in that cooling tower, so we need to cool the water, right? So the hot water temperature is transferred to the atmospheric air. Then we have the heat exchanger, air preheater. So in that heat exchanger, the temperature of the flue gases is transferred to the combustion air. So the thing is, we have to transfer heat with some apparatus. So there will be two different temperature in that apparatus. Then we have we have different types of heat exchangers. So although heat exchangers come in every size and shape imaginable, there are two basic types. Actually, these two are basic types. Then the one is tube and shell heat exchanger. Then we have another type of plate heat exchanger. So these are actually mainly um, basic types of heat exchangers. So tube and shell heat exchanger, then plate heat exchanger. Then this is the diagram of so the tube and shell heat exchanger will be look like this. So the most common type of heat exchanger is this tube and shell heat exchanger. Then the system consists of a set of tubes enclosed in a cell. So actually this is the outer shell. So inside of the cell we have the tubes. So then the tube and shell, the fluid flowing inside the tube is called a tube side fluid, and the flowing on the outside of the tube is called a shell side fluid. So we can classify uh, the flow of fluid in the tube and shell heat exchanger. So we have tube side fluid, then we have shell side fluid. So if the fluid is passing through the tube, we can call that by tube side fluid, and if the fluid is passing through the shell side, we can call that by shell side fluid. Then the tube side fluid is separated from the shell side fluid by a tube seat, that you know. So we can flow the fluid in the tube as well in the shell. Then the tubes are rolled and pressed, fitted or welded into the tube sheet or to make a leak proof. So actually these were separated. The tubes and the cells were leak proofed. Then the higher pressure fluid is directed through the tubes, and the lower pressure fluid is circulated through the shell side. Then this is based on the economy considerations, as the tubes can be made to stand a higher pressure than the cell. So of the heat exchanger at a much lower cost. So we can use both the tubes as well as the cells to transfer heat. So whereas the high pressure fluid is directed through the tubes, because the tubes having that much capability. Right. So actually this is the diagram of a tube cell heat exchanger. So there is a cell. So we can also flow the fluid with the use of cells. Also inside the cell, yes, you can see this. So inside the cell we have tubes that can be used to flow the fluid inside the cell. Right. So these are some uh, parts of the heat tube and cell heat exchanger. Just you can can see, go through that. Just drain inlet, then we have safety valves, then we have steam inlet, then we have air vent, then we have steam inlet, then we have tube sheets, then we have water box, dryer plates. So actually these are the arrangements of tube and cell heat exchanger. Then we have another type, is called plate heat exchanger. So like tube and cell heat exchanger. So the main agenda of this plate heat exchanger also to transfer heat. Instead of tube, we will use plates to transfer heat because the plate having more surface area. So a plate heat exchanger employs the plates instead of tubes to separate the hot and cold fluid. Because of a large surface area, plates provide an extremely large heat transfer area. So we need more surface area to transfer heat, that you know very well. Then we have the plates are smaller than tubular heat exchanger of the same capacity because of the large heat transfer area of the plates. Then the plate heat exchangers are used for comparatively low pressure process. Then the reliability of the plates is less in context to leakage as the large gaskets used between plates. So there are also some plate heat exchanger with the large gaskets to provide the leakage, provide the sealing of the plate heat exchangers. That you know very well what is gasket. So gasket is made up of rubber. So can provide that gasket in the plate heat exchanger to avoid the leakage of the fluid. Then this is the diagram of the plate heat exchanger. So instead of tube, we can have the plates. So the plates were attached in the heat exchanger to transfer heat. So in that we can pass two different fluids. So the red color will mark high temperature fluid, and this blue color having low temperature fluid. So if that fluid is passed through this heat exchanger, so the high temperature will be transferred because these two were attached together. Then these because of the high surface area, this temperature will be transferred to the lower temperature fluid. Right. So then according to some so we can also classify the heat exchanger uh, on the basis of flow configuration as well as the regeneration. So if you want to classify based on this flow configuration and regeneration, we can classify that by if taken the flow configuration, we can classify that by three. Is one parallel flow, then we can have counter flow, then we can have cross flow. So based on the flow, that you know, I think you can deeply study this flow, parallel. What is parallel flow? Then what is counter flow? What is cross flow in your fluid dynamics subject? So we no need to go much on that. So we can just have the types of the heat exchanger. So based on the flow configuration, we can classify the heat exchanger by three. So one is a parallel flow heat exchanger. Then we can have counter flow heat exchanger. Then we have cross flow heat exchanger. Then what is parallel flow heat exchangers? So in parallel flow heat exchangers, both hot and cold streams enters the heat exchanger at the same end and travels to the opposite end in parallel stream. So the thing is, we have to pass the fluid parallelly. Okay, so we have to give the both high temperature fluid and low temperature fluid in one side, and we have to take the both in the another side. Then the energy is transferred along the length from the hot to the cold fluid, so that the outlet temperature asymptotically approach each other. Then parallel flow results in rapid initial rates of heat exchanger near the entrance, but the transfer rates rapidly decrease as the temperature of two streams approach one another. So the thing is, we can transfer heat if you pass the fluids parallelly. Then hottest cold fluid temperature is less than the coldest hot fluid temperature after the heat exchanging process. Right, so this is the line diagram of the parallel flow heat exchanger. So we can pass cold fluid as well as the hot fluid in one end, and we can get the cold fluid and hot fluid in another end. So if that is the case, we can have this type of temperature heat transfer occur. So the initial temperature of the cold fluid is 70 degrees Celsius, and if initial temperature of the hot fluid is 90 degrees Celsius. So if you pass it through this heat exchanger, we can get this reduced temperature. So this high temperature is transferred to the low temperature fluid. So this high temperature will be reduced to 82 degrees Celsius. Then this 70 degrees Celsius will be increased to 78 degrees Celsius. So there is a increase in temperature in the cold fluid, and there is a decrease in temperature in the hot fluid. Then in a counterflow heat exchanger, so this is the parallel flow. So the opposite of the parallel flow is counterflow heat exchanger. So in just note that in parallel flow we have to pass the fluid from one side. We have to pass both the fluid from one side, and we have to take the fluid from another side. The opposite of the parallel flow is counterflow. That is, we have to pass the one fluid in one side, the another fluid in another side. Right. So you can discuss that in counterflow heat exchanger. So in a counterflow heat exchanger, two streams enters at opposite ends of a heat exchanger and flow in parallel but opposite direction. Right. So the thing is, the uh, the fluids will flow parallelly, but the direction of the flow will be the matter here. So in parallel flow, there is a parallel direction. The direction will be in one side. Both the fluid will be in one side. Where in the case of counterflow, the directions will be in opposite side. Right. So the temperatures within the two streams tend to approach in a nearly linearly fashion, resulting in a much more uniform heating pattern. So in contrast to the co-counterflow, the counterflow heat exchanger can have hottest cold fluid temperature greater than the coldest hot fluid temperature. So in that parallel flow, we can have hottest cold fluid temperature will be less, and the coldest hot fluid temperature will be more. But in the case of this counterflow heat exchanger, we can have the hottest cold fluid temperature high, then we can have the coldest hot fluid temperature less. Yes, so this is the flow line diagram of the counterflow heat exchanger. So we can the one fluid is we can pass this one fluid in one direction, in the another fluid in opposite direction, also the flow direction. So we can look this one. So the flow direction is opposed, right? So this is if the flow of cold fluid is the east side, we have to pass the hot fluid in the west side, right? So the thing is, the counterflow, there is that opposite direction. Then also there will be a parallel heat transfer, right? So this, I think the same temperature used here, right? So right, so the initial temperature of the hot fluid is 90 degrees Celsius, and the yes, initial temperature of the cold fluid is 70 degrees Celsius, and the final temperature of the hot fluid is 82 degrees Celsius, and the final temperature of the cold fluid is 78 degrees. But the direction of the flow matters here. The direction is this actually this temperature gets reduced because in this direction, but in cold fluid the direction is in this direction, right? So the cross flow exists when one fluid flows perpendicular to the second fluid. In this arrangement one fluid flows through the tubes and other fluid flows around the tubes at a 90-degree angle. So this you can refer this. Right, so this is another type. So actually this is the in both the counter flow and parallel flow, the flow is 180 degree or 0 degree, right? So the direction of the flow is parallel. So there is degree. So in parallel flow there is 0 degree. In counter flow there is 180 degree. Where in the case of cross flow heat exchanger, we have to cross by 90 degree, right? So we have to pass the both the fluid by 90 degree. They find applications when one of the fluid changes states. Example, boiler and condensers. So in boilers and condensers, we can have this cross flow heat exchanger. So this is the flow diagram. So we can pass one fluid in this direction. We need to pass in another fluid in the direction 90 degree with respect to the flow of one fluid, right? So if that is the case, we can have this kind of heat exchanging. So the initial temperature of the cold fluid may be here, and the the initial temperature of the hot fluid may be here. Then there will be a uh, sudden increase in temperature in the cold fluid, and there is a decrease in temperature in the hot fluid, but in this manner, in this path. You know what is path, or you know what is states, right? So these are the states and these are the paths. So this is the diagram of the cross flow heat exchanger. So we can get maximum 61% of the efficiency with this use of cross flow heat exchangers, right? So we can apply the first law of thermodynamics for the heat exchangers to get them some derivations. So for the first law of thermodynamics, that is Q dot minus W will be equal to delta H plus delta KE plus delta PE. So this is the steady flow energy equation because the heat exchanger is a steady flow adiabatic device. Then what is delta H, what is Q, what is W, then what is KE, and what is PE. Here the delta H change in entropy is 0. Then we can have the equation as, then under there is no work, there is no kinetic energy, there is no potential energy. The equation will be Q dot will be equal to delta H. So delta H also 0. So we can have Q dot will be equal to 0, right? So this also delta H is equal to 0. So we can have delta H, that is delta H in hot fluid plus delta H in cold fluid will be equal to 0 because we are using two different temperature fluids, right? So also we can write the equation as we can take one fluid in one side, we can take another fluid in another side. So LHS and RHS. So there will be delta H cold fluid will be equal to minus delta H of hot fluid. So this negative sign shows that the enthalpy of a hot fluid is decreasing, right? So right, you know very well. So in hot fluid, the enthalpy gets decreased. That enthalpy is given to the cold fluid. Then the rate of enthalpy decrease of hot fluid will be equal to rate of enthalpy increase in cold fluid, that you know, because there is no the system is insulated, right? So the energy balance equation or a heat balance equation can be written as like this. So that is, you know, MCP delta T. MCP delta T, that can be written as MH. So MCP delta T for the hot side, and we can have a MCP delta T in a cold side in its watts. What is MH, what is CPH, you know, what is MC. So H stands hot fluid, C stands cold fluid, and we know what is my M is mass flow rate. Then we know CP, specific heat capacity of specific heat capacity. Then we know what is T. So we don't need to discuss that. So the temperature profile of fluids in heat exchanger can be also discussed. So in parallel flow, we can have a hot in, we can have a cold in. The temperature of the fluid and cold fluid can be taken as TH. I stands initial inlet, right? So this temperature of the output can be taken as TH exit, then TC exit. Then there is a change in temperature, that high temperature fluid will transfer temperature to the low temperature fluid. Then in between there is a wall separation, that can be called as wall of separation. Then so this DQ1 stands the initial stage, and this DQ2 stands the final stage. Right. So we no need to discuss more on that. We know very well. Then we have to consider the length of the heat exchanger. That is the matter here. So based on the length of the heat exchanger, we can get different temperature. So if the length is less, we can only transfer less heat. If the length is more, we can transfer more heat. We know very well what is steady flow, right? So this is the diagram that you know that we discussed. So temperature, initial temperature of the hot fluid and cold fluid will be here. Then if that passes through the parallel flow heat exchanger, we can have this kind of diagram. So the direction will be same, right? So this is the temperature profile of fluids in parallel flow heat exchanger. Then if that is the case, the different heat transfer rate between hot and cold fluid varies with x. X is the distance, there is length, right? So if there is a minimum distance, if there is a minimum length of the heat exchanger, then we can transfer only minimum temperature. If the length is more, we can transfer more, because that we can have DQ1 and DQ2. So if the x is here, we can have a different heat transfer. If the x is here, we can have a different heat transfer, right? So from inlet to exit, because the delta T, the temperature difference between hot and cold fluid changes from one location to another location of the heat exchanger. The differential heat transfer, that is a TQ1 at section 1, just you can imagine the figure, right? So this one. So this DQ1 at this section 1, will be more as compared to differential heat transfer dq2 at section 2.22 because the delta T at section 11 is more than in the section 22. So here the comparison with of the change in temperature. Just you can refer this. So there is a change in temperature. So the high temperature is more. Here the temperature is less, much less. Where in the case of this section 22 at state 22, the change in difference in temperature is less compared with the section 11. Right. So that was stated here. Then a differential heat transfer is given by, we can have the delta dq equal to u into delta T dA. Right. So we can have, I think you know this equation. So q will be equal to u delta T into A. So where u is overall heat transfer coefficient in watts beta squared by Kelvin. Then we can write this u by inverse. So 1 by u clean will be equal to 1 by h1 plus 1 by h2. So without scaling of the surface of the pipe. So you know what is scaling? So, scaling or say, so scaling will be happen in the steel pipes or any metal pipes because of oxidation. So you know, so if the pipe is clean, we can have this u equation that by 1 by u clean will be equal to 1 by h1 plus 1 by h2. So if there is scaling or deposits, we have to consider that also. Right. So you know very well, dA will be differential area of heat exchanger. Then you know delta T is equal to change in temperature, that is at Th minus Tc. Right. So if there is a scale or impurities or deposits, so we have to consider the falling factor. So it is the factor which takes into account the thermal resistance offered by any scaling or deposits that is formed on the surface of the pipe, either on hot side or cold side. So we are using the metal pipes in the heat exchanger. So there is a chance to scaling or deposit the deposits over the surface. So that will uh, affect our efficiency of the heat exchanger. So that too can be considered. That too should be considered, right? So if there is a scale or deposit, we have to consider the falling factor. So the unit of this falling factor is meter square Kelvin by watts. So the falling factors u may be obtained from 1 by dirt. 1 by dirt is equal to 1 by h1 plus 1 by h2 plus f1 plus f2. So because we have two different types, so we have two different flowing channels. So there will be falling factor 1 and falling factor 2. So the falling on the hot side can be considered as f1, and falling on cold side can be considered as f2. So if that is the case, we can write the equation by 1 by dot will be equal to 1 by clean plus f1 plus f. So we can, so we know very well. So 1 by h1 plus 1 by h2 is equal to 1 by clean. Right. So we can write the final equation as 1 by u dot will be equal to 1 by u clean plus f1 plus f2. So f stands falling factors. Right. So for counterflow, the same equation can be written as, and the temperature profile can be taken as like this. So the hot fluid temperature Thi, then the cold fluid temperature, that was in opposite side, right? So the cold fluid temperature in. So this is the inlet of the hot fluid and cold fluid, and these were the inlet of these were the exit of the cold fluid, hot fluid and cold fluid. So the opposite directions, the opposite sides, also the opposite directions. right? So you know very well, as in the previous case, dq1 and dq2 will be differ in both the sides. So this is the temperature profile of the counterflow heat exchanger. So there is some limiting case. So this TCE, that is temperature of the cold fluid exit, can be greater than the temperature of the hot fluid exit in counterflow heat exchanger only when infinite heat exchanger area is provided. So we can increase. So we can get this case if you provide the infinite heat exchanger area. So the thing is, we are reducing the heat, we are transferring the heat. The variant of delta T with respect to the X is less pronounced in counterflow heat exchanger as compared to the to that in parallel flow heat exchanger. Hence, the heat transfer in counterflow heat exchanger is having lesser irreversibility associated with it compared to that in parallel heat exchanger. Therefore, the thermodynamically counterflow heat exchanger is more effective than parallel flow heat exchanger. Right? So you know very well, the because of the forced direction of the fluid, can have high efficiency in this counterflow heat exchanger. So hence, for the same heat transfer area provided in both the heat exchanger, counterflow heat exchanger can have higher heat transfer rates than parallel flow heat exchanger, provided both the heat the same because of the direction. Right. So, so this is the comparison between the counterflow and parallel flow. So this mean temperature difference can be calculated for both the flow heat exchanger. So you know what is mean temperature difference, right? So there is temperature difference, yes. So if you consider the hot fluid and cold fluid, there is a temperature difference that can be considered to calculate the mean temperature difference, right? So from equation 2, that was total that was in this equation, this one. So dq will be equal to u into delta t into dA. The heat transfer rate in heat exchanger can be included. So we know this capital Q will be equal to integration of. So if you want if you integrate this one, we can get the capital. Yes, if you integrate, we can get the capital Q. So capital Q will be equal to integration of U delta T dA. So this integration can be from inlet to exit. The mean temperature difference is the temperature is a parameter which takes into account the variation of delta T with respect to X. Right. So based on the length, we can have a different heat transfer. So we are integrating that one. So we can have the final equation. If you integrate, we can have this equation. Capital Q will be equal to U into A into, so because these are the constant, right? So we can take outside, then we can have final as delta T M. So here A stands for the total area of heat transfer in the heat exchanger. Then if you compare this Q, so this equation 3 and 4, this will be equal to this one. So Q, and if you compare these two, so UA delta Tm will be equal to integration of inlet exit U delta T dt. So if that is the case, we can cancel the U's, we can cancel the U's, we can cancel yes, only we can cancel U. Then we can have A into delta T M will be equal to integration of delta T dA. So that can be written as, so this delta T M can be written as 1 by A into delta T, integration of delta T into dA. Right. So to derive for mean temperature difference, so this equation, this delta T M stands mean temperature difference, right? So this is the general equation for the mean temperature difference, that is delta T M will be equal to 1 by A into integration of delta T dA, right? So we can have that for the both the hot flow that is parallel flow heat exchanger as well as the counter flow heat exchanger. So in first case we can derive a mean temperature difference as of a parallel flow heat exchanger, that you know. So this is the diagram for the parallel flow heat exchanger. Then this B. So B is the width of the plate perpendicular to the plane of the figure. That is B. Right. So then just consider, right? So this let B equal to width of the plate perpendicular to the plane of figure, right? So this width, right? So this width can be taken as B. Then other terms you know very well, MH, CPH, MC, then CPC, that you know very well. Then consider a differential area of a heat exchanger of length dx, through which the differential heat transfer rate between the hot and cold fluid is dq. So we are going to consider only this dx and dq. So dx stands smaller change in length, and dq stands change in temperature, right? So if that is the case, we can have the dA, that is area, will be B into dx. So area we know. So if you take this portion alone, the area of this portion can be the bed B, length in the breadth, right? So here we have dx as length, and the breadth we have B. So change in area will be B into dx. Then that can be used for the in the equation. dq will be equal to U into delta T into dA. So for that dA we can substitute this B into dx. Also we can write the dq will be equal to minus h minus m cp delta T or dt. So this is for hot fluid, and this plus in the cold fluid. So delta T will be equal to Fx, that is a function of, so change in temperature will be a function of x. So x based money, the temperature will vary, right? So as I said earlier, based on the length, the temperature, change in temperature will be happen. So the delta T will be equal to function of x or function of length. So x here is length, right? So if the x is 0, the delta T equal to 0, that is delta T in inlet can be considered as delta H inlet minus TC inlet. This temperature, right? So this minus this, right? So at this state, the if x is 0, this can be only this, right? So TCH minus THI minus TCI. So if the x is L, the delta T will be that is exit, right? So will be this one, THE minus TCE. The thing is, the delta T can be TH minus TC, right? So the thing is TH minus TC at any state. So if 1 is the state, we can have the inlet, and if 2 is the state, we can have exit. If the x is in between, so we can have a different change in temperature, right? So that can be, so if you differentiate this equation, if you differentiate this equation, we can differentiate that by d into delta t equal to d into th minus t into minus d into tc. This is called temperature. So this can be implemented. This th can be taken from here. Where is here? Yes. So if you substitute that, so we can write that by minus dq by mcp h minus dq by mcp c. This equation were introduced here. So then we can write that equation. We can take dq common, then we can have 1 by mcp h plus 1 by mcp c. So also we can implement this, dq will be equal to u into delta t into b dx taken from this. So that can be substituted. Then we can have the equation like this. Then we can also, minus d delta t can be written as like this. That is so this can be taken in the denominator, then integration in the both side, so we can have if you integrate this LHS, we can get this ln delta t1, that is delta t initial divided by delta t exit, inlet by exit. Then if you integrate this RHS, you can have u capital B, then yes, thus L is the 0 to L, we are integrating 0 to L. So we can have UVL into 1 by MCBH plus 1 by MCPC, hot and cold. The thing is L is added here, right? So this we know capital Q is equal to MCP delta T inlet, and capital Q for cold fluid is also MCP delta T for inlet. So that can be substituted here. So like this one. So if we substitute, we can get the equation finally as ln delta t inlet by delta t exit will be equal to u into that thi minus thi by q plus tce minus tci by q. Right, I'm repeating. So ln delta t inlet by delta t exit will be equal to u into a. So this is important equation. So u into a into th initial, that is inlet, minus th exit, that is temperature difference. Right? So temperature difference in the hot fluid and temperature difference in the cold fluid. TCE exit minus TC inlet divided by Q plus Q, right? So the thing is, hot fluid also to be considered and cold fluid also to be considered. So calculate the mean temperature difference. So here we have logarithmic mean. So because of that, we can call that by logarithmic mean temperature difference, LMTD. Right. So then also we can reduce that by so U is Q here is common. So this is a general term. Just you have to remember that. So here U is common. Then we can take that by outside. Then we can have U A by Q into change in temperature at the inlet minus change in temperature at the exit. So yes, so we can take this Q in the LHS. Then we can bring down this LHS to the RHS. Then finally we can have the equation Q will be equal to UA is delta Ti minus delta Te divided by ln delta Ti by delta Te. Right. So on comparing the equation 4 and 5, so previous equation and this equation, we can have this Q will be equal to U into A into this one delta T m. So this can be written as delta T m. That is delta T m will be equal to delta minus delta T e divided by ln delta T I divided by delta T e. So this is the equation, final equation of the logarithmic mean of temperature difference. Logarithmic mean of temperature difference LMTD for parallel flow heat exchanger. Right. So this LM or M stands logarithmic mean. So if there may be a chance to denote LM or M or they may give LMTD, right? So this delta T M stands logarithmic mean of temperature difference. So that will be equal to delta T initial minus delta T exit, sorry, delta T inlet minus delta T exit divided by ln delta T inlet divided by delta T exit. Right. So this is the equation for parallel flow heat exchanger. So that too can be derived for the counter flow heat exchanger in the following slides. So we know, so in this previous case, the counter flow is in opposite direction. The temperature profile will be differ. So this is the high temperature fluid inlet, and this is the low temperature fluid inlet, and this is the low temperature fluid exit, and this is the high temperature fluid exit. Inlet and exit can is in opposite direction, and the temperature difference. So here, so if you take 1 the temperature difference delta T will be Thi minus Tce, and in the exit, sorry, in this section 2 we have delta T as a The minus Tci, and the thing is delta T exit will be delta H minus delta Ci inlet. Exit and inlet also will be changed. Right. So if that is the case, we can write this LMTD equation for the counter flow as like this. So this delta T m will be equal to delta Ti minus delta Te divided by ln delta Ti divided by delta Te. So we know very well how the delta Ti will be and how the delta Te will be. So delta Ti will be Thi minus Tce. Then in the case of parallel flow, this delta Ti will be Thi minus Tci. Right. So just don't get confused. So if you study by comparatively, we can easily remember these equations. Right. So in parallel flow, so the I will be I. So delta Ti can be calculated with the Thi minus Tci. So whereas in the case of a counter flow, this delta Ti can be calculated with the Thi minus Tce. Right. So just remember that. Then we can move. So we have some notes. So even though the equation LMTD is the same in both the parallel and counter flow heat exchanger, the equation, the definitions of delta Ti and delta T are different for both of them that we discussed. So then this delta Te may be more than delta Ti in counter flow heat exchanger. Just if you can compare that one, delta Te will be more. So actually this is less, right? This is less. and this is more. Then there is some special cases in this logarithmic mean temperature difference. So if one of the fluid undergoes phase change like steam condensers or evaporators or boilers, so we have the thing is if what will happen if the fluid undergoes a phase change. You know very well what is phase change. So here we are using fluids. So there may be a chance for phase change. So if that phase change occurs, how can we calculate the LFTD? So for a steam condenser, so the temperature difference will be like this. So the saturated temperature, then the for high fluid, and the this is for a low cold fluid inlet. So saturated means there is no temperature difference. The temperature will be equal throughout the flow. What is saturation? Saturation means beyond that there is no increase in temperature or decrease in temperature. Right. So we can have just refer the steam condenser, right? So this is the principle of steam condenser. So in steam condenser, just we are passing steam. So that steam having only saturated temperature. So that saturated temperature is transferred to the this cooling fluid, right? So the actually the cooling water having less temperature is get transfer the heat from the steam, and exit will be the exit with the high temperature. So that is for the parallel flow. Then if that is the case for counter flow, so this diagram will happen. So this temperature of the cooling water will be less, and the exit temperature of the water will be more. This temperature increase is happening because of the heat transfer from the steam, that is saturated steam, right? So if that is the case, this change in temperature LMTD of a parallel flow will be equal to LMTD of the counter flow for this steam condenser. Then you know very well what is boiler, right? In boiler also there will be a heat transfer. So in boiler we are using steam, then that steam temperature is transferred to the hot blue gases. So this steam is having the saturated temperature through the flow. Then this temperature is transferred to the hot blue gases. The inlet of the hot blue gases will be more, and the in counter flow, this is for parallel flow, right? So the inlet will be in this direction. So this is the inlet for the steam, and this is the inlet of the hot blue gases. So the temperature of the hot blue gases is more, and yes, just the thing is we have to heat the steam with the use of these hot blue gases, right? So this temperature in the hot blue gases is transferred to the steam in the boiler, right? So inlet of the hot blue gases will be more. That heat is transferred to the steam at the exit. So that is for a parallel flow. If that is the case for a counter flow of boiler, so this is the inlet temperature of the hot blue gases. So this is saturation inlet temperature of the steam. Then this is the exit temperature of the hot blue gases, and this is the exit temperature. So if that heat transfer happening, only we can maintain the saturation of the steam. So this saturation temperature of the steam is maintained because of this heat transfer from the hot flue gases. So if that is the case, we can compare that LMTD of a parallel flow will be equal to LMTD of the counter flow, also in the boilers. So whether the change of a phase occurs, the temperature of a fluid does not change. When one of the fluid is undergoes phase change, it does not matter what kind of heat exchanges is to be designed, because LMTD value is same in both the cases. Right. So the thing is, just you have to remember that LMTD for counter flow also will be equal to LMTD of the parallel flow in both the cases, boiler as well as the steam condenser. So when both the fluids have equal capacity rates, that is MCP of both the fluids. In counterflow heat exchanger, then from energy balance equation we can have the equation as, like previous case, MCP delta T H will be equal to MCP delta T C. So from that we can cancel. So this MCPH and MCPC is equal, means we can just cancel. So then we can have delta T, that is THI minus THE will be equal to THE minus TCI. Then we can have this equation. So this delta TI will be equal to delta TE. Right. So this change in temperature in the inlet will be equal to change in temperature in the exit. So then this LMTD for counterflow can be written as this delta T. That equation we know very well. This is for any cases. So this LMTD for parallel flow equation and counterflow equation will be same for any cases. So delta Ti inlet minus delta T exit divided by delta T ln delta T I inlet divided by delta T exit. So this is the equation, same for the all the cases. Then so this will be equal, right? So if delta T is delta Ti will be equal to delta Te, so this minus this will be 0, and also this by this divided by this also will be 0. Then we can write the equation as 0 by 0. Then from L hospital rule, just from L hospital rules, then this delta T, there is LMTD for counterflow will be either this in inlet temperature difference or exit temperature difference. This counterflow LMTD also, that is T delta Ti will be THI minus TCE. Then this delta TE will be THE minus TCI. That you know very well for counterflow equation. So so during, if you consider that the above cases, we can design the heat exchanger. So this design of heat exchanger can be happen with the consideration of the followings. So if any design of a heat exchangers, first it is required to find the area of the heat exchanger, and we could find the length of the heat exchanger and diameter of the each tube of the tube numbers of the tube required. So this to be considered while designing the heat exchanger. Then to find the area of a heat exchanger, that is to find the area of the heat exchanger with the LMTD method. So they gave both the mass flow rate of hot and cold fluid, then both the specific heat capacity of the both fluids, then overall heat transfer coefficient of the fluids, then only 3 temperature among 4 temperatures. That is, if that is the case, so if they gave this data, then if you want to solve any another temperature means, so we have to find the fourth unknown temperature from the energy balance equation. Then we can use the energy balance equation. So MCP delta TH will be equal to mCp delta TC. Then if you want to draw the temperature profile of a fluid based on what type of heat exchanger is to be designed, so we know how to draw the temperature profile for the both parallel flow heat exchanger as well as the counter flow heat exchanger. Then we have the LMTD equation. Then we can substitute the known values to be found the LMTD. Then the calculate the heat transfer rate between the cold fluid and hot fluid can be used this equation. This Q will be equal to mCp delta T. Then also we can obtain the area of the heat exchanger by using this equation. U A is equal to U by U into LMTD. Okay, so if the problem is given, yes, we can solve. We can solve this by this manner, and we can design the heat exchanger. So for the same hot and cold fluid, and for the same mass flow rate of both the fluids, and for the same inlet and exit temperature of the fluids, LMTD value for counterflow heat exchanger shall be more. Counterflow heat exchanger shall be more than the parallel flow heat exchanger, that you know very well. Why? Because the opposite direction. So for the same heat transfer rate required, the area of a counterflow heat exchanger shall be lesser than the parallel flow heat exchanger. Right. So for the same heat transfer rate, so if the heat transfer is same, so that will be opposed. Okay, so the effectiveness of the heat exchanger, that is effectiveness of a heat exchanger is defined as the ratio between the actual heat transfer rate between the hot and cold fluids, and the maximum possible heat transfer rate between them is denoted by effectiveness. You know what is how effectively the heat transfer is happening in the heat exchanger can be denoted as effectiveness eta. So that can be calculated by Q actual by Q maximum. Right, so Q actual by Q maximum, where Q actual will be mCp delta T exit equal to mCp delta T is for cold fluid and hot fluid. If the fluid is condensing, then this will be 1. Right? So the Q actual will be Q maximum. So the Q actual will be m into delta H. So this H can be calculated, that you know very well. The property tables and chart, H is equal to HF plus X into HFG. That you know X, what is X, what is HF, what is HFG. Then we can calculate this X. We know we can calculate the X and we can substitute. Then we can calculate the H. Then this Q maximum is maximum possible heat transfer rate. So that can be calculated with the mCp. mCp into delta T. So here mCp is small compared with the change in temperature. Then we can have the mH and mCpH and mCpC. Then the capacity ratio. This is the ratio between the smaller capacity rate to the bigger capacity rate of the heat exchanger. So that can be written as C will be equal to mCp smaller and the mCp higher. So the value of C varies between 0 to 1. So the capacity rate ratio will be 0. So if mCp higher is infinite, or if one of the fluid is changing its phase. So if there is a phase change, this C value will be 0. So the example of these conditions are so this can be happen in the condenser, evaporator and boilers. Then the another term in this heat exchanger is this NTU. NTU stands number of transfer units. So over this NTU signifies the overall size of the heat exchanger because it is directly proportional to the area of the heat exchanger. So this can be given as UA divided by MCP small. Right, so the effectiveness in terms of NTU, so for parallel flow heat exchanger, the effectiveness will be the 1 minus E into E power 1 plus C into NTU divided by 1 plus C. If that is the case for counterflow, the effectiveness of the counterflow can be written as 1 minus E minus E power minus 1 minus C NTU divided by, instead of 1 plus C, we can write as 1 minus C into the same E power minus 1 into 1 minus C divided by N into NTU. Right, just remember the equation. We don't need to derive the equation, just to have the equation. If any problems with this equation, just you can solve. Right, so there is some general cases when one of the fluid is undergoing change of phase, like boiler and condenser and the evaporator, then C will be 0, that you know very well. So if that is the case, if C is 0, we can write the effectiveness E will be equal to 1 minus E minus NTU E power minus NTU. Then for counterflow, effectiveness will be equal to 1 minus E power minus NTU. So because C here is 0. Right, so if both the capacity rates are equal, so if C is 1, we can rewrite the effectiveness E for parallel flow as 1 minus E power minus 2 NTU divided by 2. For counterflow, that will be 0. So for from else hospitals rules, so we can have the for effectiveness for counterflow will be equal to NTU divided by 1 plus NTU. So if for these cases, if C is 0, we can rewrite the same equations like this, and if C is 1, we can rewrite the same equation like this. Then the effectiveness NTU method is mainly used whenever both the exit temperature of hot and cold fluids are not known for the given heat exchanger area. Right. So if there is if the in some other cases, there may be chances without this THE and TCE. So if that is the case, we can use this NTU effectiveness method to design the heat exchanger area. Right. So there is some additional concept also. To reduce the length of the heat exchanger, passes are required. Right. So we can reduce the heat exchanger length, but we need more passes. Passes means the poles of the tubes in the heat exchanger. Also, passes are required when the heat transfer area required is less large, like in case of power plant condensers. So if you consider the power plant condenser, the area will be the yeah. So if you consider the power plant condenser, so in that power plant condenser, the passes will be more to reduce the length of the heat exchanger. Then the diameter of each tube of the heat exchanger can be determined for the area of a heat exchanger. So yes, the diameter also will be the matter while designing the heat exchanger. So the area of heat exchanger can be, so if you use the circular tube, you can calculate the area of a heat exchanger by using the pi dl equation. So that can be calculated by dl into n into p. So all should be considered. So pi d is the area of the circle. Yeah, then length of the tube can be considered, and the n is the number of passes. Then this P is the number of passes in a heat exchanger, and N stands for number of tubes. Right, so number of tubes also will matter. So we can use a single tube, also we can use multi tube. Just we can consider. Right, so this is the outline of the LMTD. So hot fluid between hot and cold steams due to heat flows between the hot and cold steams due to temperature difference across the tube, acting as a driving force here in the heat exchanger. Then the temperature difference will vary along the length of the heat exchanger. Then this is the comparison between these two parallel flow and counter flow heat exchanger. Right, so then the integrate average temperature difference for either parallel or counter flow can be written as the equation as theta 1 minus theta 2 divided by ln theta 1 by theta 2. The effectiveness of the temperature calculated from this equation is known as LMTD. So this theta 1 will be delta T2 and theta 2 will be delta T1, and this delta T will be change in, that is LMTD. Then each of the three types of heat exchanger have their advantages and disadvantages. Yes, of course. So of the three, the counter flow heat exchanger is greater. Yes, most effective, most efficient when comparing heat transfer rate per unit area. Then this LMTD delta theta will be equal to delta T Lm is greater than a similar parallel or cross flow heat exchanger. Then so there is some problem. So this is the given data. So T1 represents the hot fluid temperature. Then T1 inlet is 200 degrees Celsius, and T1 outlet is 145 degrees Celsius, and U is given 70 BTU, and A0 is given 75 feet square. Then T2 for cold fluid. Right, so T2 in is 80 degrees Celsius and T2 out is 120 degrees Celsius. So if that is the case, the counter flow LMTD can be calculated with the equation. Then if you substitute the values, we can find the LMTD of the counter flow as 72 degree Fahrenheit. So the problem will be like this. Just try to solve. Then for parallel flow, so the LMTD can be calculated, and that will be around 51 degree Fahrenheit. So inserting the above values into the heat transfer equation for the counterflow heat exchanger gives the following results. That is, the Q can be calculated. That is delta LMTD into area into, right. So this U into area into LMTD. So we can calculate the Q dot. Then so this is for counter flow. So this is for the parallel flow, and this is for the counter flow. The Q can be calculated. So there is another problem. So they gave some data. The flow rate of cooling water through the inner tube dA is given. Sorry, dA of the inner tube is given. Then the flowing rate Q is given. Mass flow rate is given. Then while the flow rate of oil through other outer annual, that is D outer is given, and M dot of another fluid is given. Then the temperatures T1 H is given, Tc is given. Calculate the LMTD for both co and counter flux HSX, that is heat exchangers. If the outlet temperature, yes, we discussed this problem, right? So if the three temperature is given and the others were given, so we have to calculate the LMTD. Means we can calculate the So these are the given data that you know. So 100 degrees Celsius, 60 degrees Celsius, uh, m dot of H, m dot of C, and inlet temperature of the cooling also given, then mass flow rate also given, then Cp also given. So this is Cp, specific heat of oil and specific heat of cooling water. Also we are given, I think this 2.31 Cp to be taken from the property tables and charts. So just if you leave it. Okay, 5 minutes. Yes. So this data is taken from your property tables and charts. So we can refer the property tables and chart to get this Cp value of oil and Cp value of the water. Yes. Then we can use the steady flow energy equation to calculate the temperature at water exits. Then that can be used. So this is the comparison for counterflow heat exchanger. Then this is the comparison of the parallel flow heat exchanger or co-flow heat exchanger. So the calculation means, so if you calculate the LMTD for this counterflow heat exchanger, that will be around 43 degrees Celsius. So if you calculate the LMTD for this parallel flow heat exchanger, the LMTD will be around 39 degrees Celsius. So there is a comparison. So 39 degrees Celsius, 43 degrees Celsius. Then length of the heat exchanger for can be calculated with the equation. Right. So the results demonstrate that the given of the same operating condition, operating the same heat exchanger is counterflow manner will result in a greater heat transfer rate than operating in parallel flow. Just if you compare, the same will be given, that is the counterflow is effective. So actually what is done, so most large heat exchangers are not purely parallel or counter or cross flow, rather a mixture of these of 2 or 3 heat exchangers is used, right? So there is a combination, right, for the large heat exchangers. The reason for this mixture is to maximize the efficiency of the heat exchanger within the restrictions based on the design, such as size, cost, operating pressure, required efficiency, types of fluid, cost, and temperatures. Then two fluids are made to pass each other several times within a single heat exchanger to increase the performance. Right. So there will be some more passes. So there will be some more folds. Then when the fluid pass each other more than one time, it is called a multi-pass heat exchanger. So if there is more passes, that can be called as multi-pass heat exchanger. So if the fluid pass each other a single time, it's called a single pass heat exchanger. So commonly, the multi-pass heat exchangers reverses the flow several times by the use of U tubes. Right? You know. So this multi-pass can happen with the use of these U tubes. And a second method to achieve the multi-pass is by the use of baffles on the shell sides of the heat exchanger. So this is the single pass, this is the multi-pass. Then this regeneration also can happen. The heat exchangers are also classified by the function of a particular steam system as a regenerative heat exchanger and a non-regenerative heat exchanger. So you know how we can achieve the regeneration. A regenerative heat exchanger is the one which the same fluid is both the cooling fluid and the cooled fluid. The hot fluid gives a hot heat to incoming cooled fluid, heating it and itself being cooled. usually founded in a high temperature system. Actually, this is the regenerative heat exchanger. You know how the regeneration can happen. Then for non-regeneration, so this is the flow diagram. So in a non-regenerative system, the hot fluid is cooled by the fluid from the separate system. The energy removed is not returned to the system. Right? So this is non-regeneration. So also we have another AMTD. So what we discussed is LMTD, that is logarithmic mean temperature difference. Also we can calculate the temperature difference with the use of this arithmetic mean. So that is arithmetic means that just average. Right? So just we can take the average of the based on the temperature we can have. So n is here but least accurate. So this AMTD method will be less accurate to calculate the mean temperature difference. So the equation can be, that is TPI plus the TPO, that is exit, divided by 2 minus the TSI minus TSO by 2. That is this is the temperature difference by 2. So if you add the inlet temperature and exit temperature of the hot fluid by 2 minus inlet temperature and exit temperature of the cold fluid by 2, then we can get the AMTD. Right? So the linear increase in secondary fluid temperature makes it more easy to do manual calculation. So this AMTD will in general give the satisfactory approximation. Right? So we can get approximate value of this temperature difference. So when heat is transferred as the result of a change, a phase like condensation or evaporation, we can't use this AMTD. Right, so the equation can be simplified by setting that is TP1 will be equal to TP2 or TS1 will be equal to TS2. So here TP stands for fluid and TS stands for cold fluid. Then, so if you want more clarifications about the AMTD and LMTD for the heat exchanger, just you can refer this link. So there is a comparison between the LMTD and the AMTD, and you can calculate the LMTD and AMTD if any values is given. Just go through this website. Just you can have some idea about the AMTD and LMTD for heat exchangers. Then here is the conclusion. So heat exchangers serves as the backbone of the industry in which it is used. So their effectiveness directly related to the economy of the organization and the task performed with them. So the arrangement of the heat exchangers are very important, and the proper functioning of the units are necessary as they save energy, cost, and product damage. So this is the view from the industry point. Right? So we can save the industry with the proper design of the heat exchanger, mechanical industries, right? So with this we can conclude the unit 5. Just just uh, just go through all the units. Then if you have any queries, you can ask at any time. Then all the best for your semester examination. So that's it. So do you have any queries? Just you can ask, or else you can hang up. Thank you. Have a good day.
Thank you, sir.